So we've seen how to find a cumulative probability associated with a given location. So on the last video, we looked at how to find the probability that x is less than or equal to negative 1.25 in the standard normal distribution with mean 0 and standard deviation 1. But what if instead I want to know the location, so what's the x value here, that's associated with a given probability? So I'm looking at something like this. I know the area or the probability, and I want to know what's the x value that goes here. Well, this is actually relatively simple using StatCrunch. Instead of plugging in for my x value, I'll just plug in the area. So here, if I did this in StatCrunch, I found that the z-score that corresponds to an area of 0.1 to its left is negative 1.28. That's called the 10th percentile because 10% is below that value. I could also use a table of areas to find that z-score. In this case, I know that my area that I'm interested in is 0.1. So instead of looking at the z-scores like I did in the previous examples, I'm going to look at the areas here to find the area closest to 0.1. If I scroll through, I find that 0.1 is between 0.1003 and 0.0985, and this one, 0.1003, is closest. So if I think about circling this area and looking to the left and up, I can find the z-score that corresponds to that area. So if I go to the left, I see that it starts with a negative 1.2, and if I scroll up, I see that it ends with the 0.08. So it's going to be negative 1.28. Let's look at the seal pups example again. Remember, the birth lengths of seal pups follows the model, normal model, with the mean of 29.5 inches and a standard deviation of 1.2 inches. Suppose pups with lengths at the 15th percentile and below are unlikely to survive. What birth lengths would make it unlikely that a pup would survive? Okay, our steps are going to be very similar. We're always going to start by drawing a picture. So my picture should be a normal curve because I know it's a normal distribution, and I should mark that mean of 29.5 in the middle. The next thing I want to do is shade the area that I'm interested in. I want to know what length corresponds to the 15th percentile. Now the 15th percentile means that I want to shade an area that corresponds to 0.15, okay, for the 15th percent. So the area, the red shaded area here is 0.15, and I'm trying to figure out what is the value, go down here, what is this x value that corresponds to an area of 0.15 to its left. So I'm going to go to StatCrunch to figure that out. And in fact, I called it y there on your screen, so maybe let's call it y. Okay, so we want to go to StatCrunch. Let's do that. So here's StatCrunch. Now remember, I'm going to go to Stat and then Calculators, and I want a normal calculator. So here I am. Now I want to know what's the x value or y value that has an area of 0.15 for my seal pups. So remember, my seal pups had a mean of 29.5, and a standard deviation of 1.2. So let's plug that in and hit compute. And here I'm told that 28.26 is going to be my x value or my y value. So let's go back to our slides. So if we round, we get 28.3 inches. So birth lengths less than that would be unlikely to survive. Now, how do we decide whether we should use the normal or the inverse normal process? Well, you should ask yourself, is what I know of value from my distribution and I'm looking for a probability or an area? Or is what I know a probability or an area and I'm looking for a value from my distribution? So let's try that with this example. It's known that the heights of adult men follow a normal model. For each of these situations, let's decide if you are finding a probability, so you need the normal approach, or you're finding a location and need the inverse normal approach. So our first example is a clothing store manager wonders what percentage of her customers are taller than 6 feet. Well, let's think about what the picture would be for number 1. Let me pull out. All right, so I'm going to draw a normal curve. I'd have a mean of whatever. We're not given it in this case, so let's just use mu. And we want to know what percentage of her customers are taller than 6 feet. Well, I know a height, and a height in this case is my variable, so that goes on the x-axis. And I'm looking for a percentage or an area or a probability, the percentage that's higher. So I'm looking for a probability, and so I should use the normal approach. What about part 2? A clothing store manager wants to cater to the tallest 20% of men and wants to know what heights she should accommodate. So in this case, we still have a normal curve for our heights. And the mean is somewhere here. But now we want to cater to the tallest 20% of men. So that's going to give me an area or a percentage or probability. So what I know is that this shaded region here is going to be 20% or 0.20. And what I'm looking for is the height that corresponds to this area. So this is going to require the inverse normal approach. All right. Normal distributions are symmetric and unimodal, so the empirical rule that we saw earlier this semester applies to normal distributions. Now remember, the empirical rule said that if you go 1 standard deviation on either side of the mean, that contains 68% of your data. If you go 2 standard deviations on either side of the mean, that will contain approximately 95% of your data. And if you go 3 standard deviations on either side of the mean, that interval contains almost all of your data. If you don't remember the empirical rule, I suggest that you go back and look at your notes from earlier this semester to remind yourself. So if I wanted to do that exactly, here I've got a normal distribution with a mean of 80 and a standard deviation of 4. Now we can find exactly what percentage of the data lies within 1 standard deviation of the mean by just using our StatCrunch calculator. So if I want to go 1 standard deviation to the left, I'm going to subtract 4 from 80 to get 76. 1 standard deviation to the right, I'm going to add 4 to 80 to get 84. And so I'm going to put those bounds into my normal calculator, and it tells me that the probability of being between those two values is 0.68268, etc. So approximately 68.27% of the data is between 76 and 84 in this case. I did the same thing over here, only I went 2 standard deviations on either side. So I took 80 minus 2 times 4, which is 72, and 80 plus 2 times 4 to get 88. And I plugged those numbers into my StatCrunch calculator to find that 95.45% of the data lies within 2 standard deviations of the mean. So our approximate rule from the empirical rule, our approximate numbers are really close to the actual numbers.